calculate B sub I now? That's the actual question.
Saturation.
10 volts plus VB, or minus 10 volts plus VB.
You could say, as you're saying, it's minus 10 volts plus V sub B, which is minus 10 volts, minus 4.2, which would be minus 14.2. And now now you can leave it at that, or you can basically make that kind of paper calculation, and you run the circuit in piecewise. You might find the Q2 does not actually go into saturation. So it actually needs a lower voltage on the base here in order to get 4.9, minus 4.9 on VCP. So we'll let everyone go ahead and work on this problem. I'm kind of going through the analysis of the paper. Once you're settled that you have a number for the V sub I to put Q2 in saturation, and you can try it in piecewise. And of course, if piecewise does not agree with the paper calculation, that means something else in the circuit needs to be accounted for. And there is to be accounted for. And we'll return to this later, but we want everyone to actually try out the circuit first. And then this is it's not the same circuit, but it's a push-pull with 10K, and then it's got a sinusoidal, 4-volt sinusoidal on the input. And it's basically just to view the crossover distortion on the amplifier. So it's showing here once the input gets right around this, it actually appears like it almost goes very close to 0. You have to actually mean, if we adjust the steps, basically, this is 0.4 volts here. Doesn't, these guys basically, the model actually doesn't turn off until it actually gets to around 0. And then it shows the crossover structure.
Yeah, of course.
This slide doesn't
I mean, it's
actually show the
that's a problem.
device turning off
Cutting.
at around 0.5 or 0.4 volts. But we understand from here that is what actually is happening.
The point I'm gonna they're both right, they're both out. Oh, the cutoff, that's the cutoff. That's the cutoff.
Okay, this gets into the biasing of the bipolar junction transistor. We assume it's in the active mode, and then now we want it to behave as an amplifier. So this brings up the term called biasing, and the wording here is just saying biasing for this transistor is adding 4 resistors, one resistor, 2 resistors between ground and 2 resistors connected to the battery. And then with these resistors, we can control the collector, base, and emitter voltages and current, and we can set up what's called a DC, specific DC conditions for the circuit to be in the active mode. So, and this is called the operating point. It's also called a quiescent point. And the name that we really have used before is the active mode. So when we use the word, say, active mode, we're talking about a specific collector current and a specific collector emitter voltage. And when we have those two, then we can set the transistor up to be active mode. Literally, there are hundreds and hundreds of operating points. So the idea is basically how do you go about picking the most optimum for your circuit. Manufacturers, because the manufacturer is not involved in the design of what you're working on, the manufacturer will usually supply collector curves, BJT curves. And this is an example of a curve here. So the manufacturer will test thousands of these transistors, and down to the bottom, on the X side, this is the collector emitter voltage. It's going from 0 to 5 volts. And then over here, this is the collector current on the y-axis going from 0 to 10 milliamps. So the manufacturer will vary the collector emitter voltage here and then vary the base current. And each one of these curves is a combination of collector emitter voltage and base current. You notice the base currents basically, there's very little variation as the collector emitter voltage changes. And the base current, I would take an example, here's one around 60 bases, 60 microamps. Now you can choose any of these collector emitter voltages at the lower part here, and then over here 60 microamps on the base is equivalent to around 6 milliamp of base of collector current over here. So if you're designing an operator point, you will have these curves. So you select a collector emitter voltage. Let's say we pick, just select 2 volts here, and then we draw a line up, and we intersect with this 60 microamp base current, so we're going to get 6 milliamp current. Now we need in order to get a delta I sub B and a delta I sub C, coupled with the base current here, like this goes from 60 microamps to 80 microamps, and then we get the change in the collector current. We call that delta I sub C. So let's say engineer A decides to operate their device from this point here. How many other possibilities are there on this plot for an operating point? Probably hundreds of them on these curves. So another engineer might decide I'm going to operate it here, and another engineer might operate at this point here. Now, the decision being made is to stay away from the lower base current curve. Why do we? This is a low base current, so what's the issue with operating with a low base current like this? Which mode are you moving toward with low base current? Of the three modes in the BJT.
Cutoff?
You're moving towards cutoff, so you probably stay away from this curve, and then you probably avoid this upper curve too. Why is that? Which other mode is the transistor trying to go into this very large base current? It's trying to move on the saturation, so you probably stay away from this curve. And then, in terms of collector emitter voltage, we avoid this point over here, very low VCE. This is actually where the transistor moves into saturation. When the collector emitter voltage gets to be around 0.1 to 0.2, what happens is the collector current abruptly starts to drop. And that's this knee over here. So we keep the collector emitter voltage away from 0.1 to 0.2, and then we have a realistic value of base current to get the amplifier. But, usually you're trying to operate somewhere in the middle here, but it's really restricted by your collector emitter voltage. So here's a calculation of beta from that curve. Here's a DC beta, which is just a static. ICQ is quiescent, and IBQ is the base current quiescent. So this comes, if we plot those points around 87.5. The AC beta, and when we take the delta I sub C and delta I sub B, and that's around 100. These are basically close enough so that when you're solving work with the circuit, you probably just assume that manufacturer is giving you the AC beta information. So assume active mode, and you want to determine what's the I sub C and what's the collector emitter voltage, which is the DC operating point for the transistor. And then to find out what it is, we basically use our diode assumptions. If the P-N junction is on, it's going to be around 0.7 volts across it. So this base emitter diode here is going to have 0.7 volts ideally across it when the device is on. So we're going to assume that what we're doing here, we'll assume the resistors are given. Let's assume that. So here's the equations for solving the circuit we're setting up. V sub B is sometimes just called V sub B. Doesn't always have a B. This is the voltage on the base here. And is this equation correct? What does this equation imply about the circuit? divider, and what else? And it's showing a current law is showing only two components of it. There's actually another component over here. What is, what other component should be in this equation to be accurate? Base current. This equation is assuming the base current is 0 over here. So which is probably okay to start an analysis assuming the base current is 0. And as I said, this becomes a voltage divider at this point. And then R sub B is R1 in parallel with R sub 2. And how do we get this equation? So it just says it's in parallel with. How are they in parallel? This is actually an AC alternating current equation. Whenever we solve for AC, this battery becomes a short circuit, wired to ground. So now you've got two resistors in parallel, and now we can make this assumption here. So, what it's doing is moving toward what's called a small signal assumption here. So we can get those two resistors parallel. And now, if we solve for the current over here, you notice these arrows are just saying there's no current going into the basement. In reality, it is a current. But we can solve for the emitter current here. That's in this loop here. Solve for the emitter current becomes this equation. And then eventually we get it in this form over here. You want to make sure this equation is on your formula sheet for the emitter current. If you don't have this equation, then you'll basically go back several steps and solve for the voltage drops around the spacing of the loop, which is this step over here. So I sub E emitter current is VBB minus the base emitter divided by RE plus R beta plus 1. And here, if we make V equal 10 volts with a battery V sub BB, a diode with a resistor R sub C, we came across this equation earlier, and we were reviewing current driving. We came up with this equation, we indicated that we'll meet this equation again once we get into the gain of the amplifier. So this is the same equation from this earlier current driver for an LED circuit. So this approximation for the emitter current at the bottom here, basically saying that this term R sub B over beta plus 1, if we neglect that term, we get an approximate formula for I sub E. So this is actually the preferred version of this formula. If you do solve a problem with this version, you're still in the ballpark of the correct result. However, the real equation is do not assume RD of beta plus 1 is negative. Just understand that part. So this term RD over beta plus 1, this has to do with it. And again, when we were doing the current drivers, we came up with this term weak dependency on beta here. And we went through several versions of a RV and a RE, and found combinations that show dependency of the emitter current on beta. So we're basically doing the same with this amplifier design. It comes to the point where you have to select RE and RB. You should refer back to the notes on the current drivers where we went through several versions of RB and RZE. Now this part here, R1 and R2 must not be too large. And let's say we make R1 10 meg ohm, 10 meg, and make R2 10 meg. And then we've got a 10 volt battery. So what's the voltage on the base here? R1 is 10 meg ohm, R2 is 10 meg ohm, the battery is 10 volts. So what's the base voltage? What formula do we use to calculate the base voltage? We use our voltage divider equation. Now, what's the current through the 10 meg ohm R1? So you want to solve for the current through this resistor.
R1 is equal to VCC minus.
R1 is equal to 10 volts minus 5 volts divided by 10 meg ohms. So what is that number on the calculator?
5. Five nine.
Around 500 nanoampere.
Oh, wait.
And it says
Oh,
that
oh.
it says from the battery there's only 500 nanoamperes of current available, and resistor R2 will take some of that current. Overall, it means there's no current left for the I sub D. So the circuit would not work because there's not enough current in the voltage divider to drive the base segment. So that's what we say. You don't want to make those two resistors too large. 10 meg ohm is down. These resistors are probably under 200K or even under 100K, depending on the current in the transistor. So here's an example of a circuit. The battery is 12 volts here, R1 and R2 are 20 k ohms, and RE is 5.3 k ohms. So do we agree with this equation? This calculation. And is it correct? It's not showing the kilo ohm and milliamp units. It says the base voltage is half of 12, which is 6 volts, minus the base of 0.7 divided by 5.3 K plus 10 over beta plus 1. 0.98 milliamp, and if we remove this term, it comes out around 1 milliamp. So it's not much difference between the two. So in terms of, now how would we get the collector emitter voltage? Remember, we have to solve for I sub E, I sub C, B sub C, B sub E, and then B sub sub B. So all we have now, we have I sub E, we have V sub B. How do we get the collector voltage? And of course, we need R sub C to do that. Then how do we get this voltage on the collector?
C is equal beta minus V sub E is equal to inversion something more.
Now, if we can assume alpha is equal to 1, which is not accurate, or we can try to solve for the base current, which will be more accurate. However, it's going to involve a couple more calculations to actually do that. But we have I sub E, and we have V sub E. What's the voltage on the emitter here? It's a 5.3 k resistor, so what's the voltage on the emitter?
5.3 minus 5.3.
Now, we could have 6 minus 0.7 on the emitter, or you could solve IE times RE, so you can actually get two numbers and decide on which one you're going to actually use in the calculation. All right, this is just reviewing the current driver. RE should be much greater than RB over beta plus 1, and that gives us the weak beta dependence here. The base voltage must be greater than the base emitter, which is 0.7. And we were talking about solving for this voltage here. The collector resistor is to give the AC gain in the circuit. And R sub B, which is R1 in parallel to R2, we use that to get the input resistance. And then there's a kind of a rule of thumb here. The collector emitter voltage should be between the battery divided by 3 and the battery divided by 2. And the engineer would decide on which one of these to actually implement. Usually the battery divided by 3 because you have 3, you have a voltage drop here, a voltage drop on the collector emitter, and then another voltage drop here. So if we put the same voltage drop across each one of these junctions, then that's using the VCC over 3. Now, selecting these two resistors, R1 and R2, more formulas that we need to have on our formula sheet. So we want to solve for R1 and solve for R2. And we take these two equations up here. This is the voltage divider for V sub VB, and then this is the parallel resistance for R sub V. And then we can basically get we can solve for R1 is RB times V sub CC over base voltage, and then R sub 2 is what's called an inverse resistor formula. And this is 1 over RB plus 1 over R1, and then we invert that. This formula is for, we have two resistors in parallel, and let's say we have R1 value. We have the value of resistor 1. We do not have the value of resistor 2, but we do have the value of both in parallel. So we have the parallel RD, and we have the single resistor R1. We can solve for this unknown resistor here's an example. Our battery voltage is 9 volts, and we want the operating point to be a milliamp I sub C. We want V sub C equal to 3 volts, and we want the collector resistance to be 3 k ohms. Assume basic emitter is 0.7 volts, and that beta is equal to 100. So how do we complete the design of the circuit? And this is the only information really given. We need the emitter resistor, we need R2, and we need R1. And then what's given though, collector current is 1 milliamp, and the collector emitter voltage, once it's designed for an operating point, is equal to 3 volts.
DC is the difference between the voltage from the collector.
And the battery is 9 volts.
For the between collector and emitter.
Now,
So it's DC by
you can't solve for the base current, do not have resistors R1 and R2. So what's probably our first step?
You can find the collector voltage, correct?
We're given a collector resistance of 3K,
And the collector current, correct?
so we're given a collector.
So,
So the collector resistor, we have the current through it, and we have the resistor side. So the collector voltage is what? What's the voltage here? V sub C.
just
6?
10, 9 volt battery minus I sub C R C.
so they
And
just
if I sub C is milliamp and R C is 3K, that's 9
Yeah.
minus 3.
6 volts.
6
So
volts.
there's 6 volts on the collector. So we have one of the, what we're doing is kind of analyzing the circuit before starting the real paper analysis. To see if some of the numbers kind of make sense. So here, just repeating the specifications. Before, we indicated that we could use the rule of thumb that the collector emitter voltage is, this voltage is equal to I sub E R E, and it's also equal to I sub C R C. So with that, we can set I sub E R E equal to battery minus I sub C R C minus V sub C E. So this is the voltage drops through the transistor to ground here. And we notice I sub C R C is 3 volts. We assume the 1/3 volts, so VCE is 3 volts. And all the numbers basically are given. And we could get this step, once we decide there's 3 volts here, we could say there's 3 volts across VCE, and then there's 3 volts across RCE. So that's what this equation is doing. And if R sub E has 3 volts across it, and we assume alpha equal to 1, what's the voltage on the emitter here?
1 milliamp?
We have 1 milliamp, and what's the voltage? 1 milliamp is 3K. There's 3 volts on the emitter. Now, the steel doesn't tell us the value of that resistor. We basically are located with I sub E R sub E, and then we basically calculate out 3 volts. Now how do we get 3 volts here? How do we get 3 K ohm here? We have 3 volts, 1 milliamp of current. So that's a 3 K ohm resistor. So we have this resistor, stop for this resistor. And your design decision is next, because we have to make a decision between R sub E and R sub D right here. So when we went over this design, you have all kinds of variations we could do. We could say this RB or beta plus 1 is 0.1 RE. That's just out of hundreds of combinations, basically. And then if we solve that, we get RB is approximately 30 K ohm. And we don't really know if it's a weak beta dependency until we basically start doing the tolerance analysis for this work we're doing here. And let's say you would pick RB is approximately 0.5. That's probably too close to R sub E to do that. So you're probably go to 0.01 RE. But again, this design is just saying, let's just say RB of beta plus 1 is 0.1 RE. And how do we get RB is equal to 30 K ohm from that? If R sub B is equal to beta plus 1 times 0.1 RE. And RE is 3 K ohm. So that's 100 plus 1 times 0.1 times 3 K. And that comes out around 30 K ohm. Now you could go back and try to test for weak beta dependency, but the problem here did not basically put that into the instructions here. So you can basically take that value of 30 K, and now solving for the 2 base resistors. Here's our one equation. This is our 2 equation here. R1 around 67.5 K, and then R2 about 20.8 K ohm. This lower one is just rounding off to a standard resistor table value. Instead of R1 68K and R2 21K. If you tried to use these values, you'd probably be trying to find 1% or better resistors. So if you want to stay with 5% resistors, you would just use standard resistor value. Now this note here is just indicating that this amplifier will operate with 2 power supplies. These come in bigger amplifiers, so we can have this number here that it's actually a plus here. We have a plus battery and a negative battery, and then we can tie the base resistance directly to ground here. So this is a dual supply sort of here, and what this does is it doubles the voltage range on the collector to keep the max and min, because now we have 2 times that. So if we have 10 volt batteries, we can get approximately maybe 18 volts peak to peak on the collector. So dual supply is the same as the single supply in terms of emitter current. So when you come across a problem like this, even though it appears to be really different from the version that we've just gone through, again, this is a plug. The emitter current formula is the come across this in some of the earlier problems with this, basically, you can decide to use the 1/3 group or the 1/4 group. And then some example circuits here. And this is a amplifier, and it says to the common emitter, beta is 200, beta emitter is 27, basically for bias. Early voltage is 100 volts. So run a DC analysis of the amplifier, show that the transistor Q point is approximately I sub C is 2 milliamp, and the collector emitter voltage is about 3 volts. So how do we get the base voltage here? Voltage divided. What do we assume for alpha? And we can use the voltage divider here. The two base resistors, 63K and 37K. This is our voltage divider. The base voltage is 3.7 volts. And now we can move over to calculate I sub E. And all the parameters are basically known. And once we solve this equation, it comes out 1.9 milliamp. That's pretty close to the design idea of 2 milliamp. And then now, RD is the two resistors in parallel with base of 23.3K. And then the next part was to solve for V sub collector emitter voltage. And that's equal to V sub battery minus IC RE minus IC R sub C. So 10 minus 2 times those resistors, and that comes out about 3 volts. So you notice this has 3 volts across it. You're not really going to have exactly the 1/3 battery rule. You probably change the batteries to maybe 12 volts to do that. So I want to make sure we really understand how, given a circuit like this, it looks very different from the circuit we've been going with. The circuit has some capacitors in it. What's the purpose of these capacitors? What's its purpose?
Filter out high frequency.
So it fills a high frequency. What else would a capacitor function as?
Maybe cause the voltage not to drop super significantly.
What type of signal will not pass through a capacitor?
DC.
DC. So it's a blocking capacitor. Over here, this is another blocking DC block. The one on the emitter, this is a bypass capacitor. Its purpose is to put a AC short circuit on the emitter to ground. And that means this emitter resistance does not influence the gain of the amplifier.
Professor?
Yes.
For the last question, for VBB, do we assume base I equals 0 on that one?
You consume alpha is equal to 1,
Mhm.
and like this example, if we assume alpha is not equal to 1, alpha is equal to 200 over 200 plus 1. And then we would get a different voltage on the base right here, because now we have base current, and now we have to resolve for I sub E. So it really just, the preference here is just to assume alpha is equal to 1. If the design specifies that you need to calculate I sub E based on beta, then that's what you would do. If the problem does not specifically indicate that, then I would just say go with the alpha approximately equal to 1.
Thank you.
There's some problems on this problem session coming in amp biasing. And the first problem on this example is it's a dual battery, positive and negative battery, and a base. Instead of two base resistors, it has one resistor to ground. Okay, the way this problem is being solved is it's not using that ISO B equation. The author here is actually solving the base emitter loop in terms of voltage drop. That's why the equations here really look quite different compared to the ones we've been going over. This actually brings up the next topic that we're going to be discussing. That's the small signal model of the BJT amplifier. So small signal, we'll take this, it's an NPN transistor, so we'll take that and convert it to what we call a hybrid pi model. And so instead of the transistor schematic, you basically build a model of the transistor. So this is the next type of analysis we're going to be going through, which is small signal. And this is a second version of a similar problem, and it's basically just, again, it asks to solve for, show that the Q point is ISO2 is approximately 1.7 milliamp, and the collector new voltage is approximately 3 volts. So the author here again is assuming alpha is a 1, and here's your base voltage calculated, and then alpha is a 1, so we can use the exact mode formula, and we find it's around 1.77 milliamp here. I'm searching for a BJT that's in saturation, and this problem here, consider the following BJT, and then VC sat is either 0.1, beta is 120, RB is 1K, RC is 1K, and then up here at the top, what it actually solves for. So it doesn't say mention assume active mode and show that it creates a contradiction. So we assume alpha equals to 1 and RE is equal to 0 and then the base voltage is base emitter is equal to 0.7. So there's no need to use the other formula to calculate. This emitter is grounded, base voltage is at 0.7, and the 4-volt battery is given here, so the base current is 4 minus 0.7 over RV, which is 1K, and that's 3.3 milliamp. That's a really large base current. And then, assuming active mode, I sub C is equal to beta I sub B, so 120 times 3.3 milliamp. That's 396 milliamp, again, a very large current. The collector voltage, so we try to find a contradiction. A large base current and a large collector current do not really give a contradiction yet. So now we try the collector voltage, V sub C is V sub CC minus ICRC, 9 volts minus 3.1K times 396 milliamp, and the collector voltage is minus 387 volts. So why is that a contradiction? It's a large number, but the large number by itself doesn't really give a contradiction.
It's less than the base voltage.
There's a note here, the base voltage is base voltage is 0.7 and the collector is minus 387 volts. That's a contradiction to the active mode. So collector is less than the base. So now, the author says now assume saturation on IB, IC, and ICB. And the original calculation of I sub B is still correct. So that's still I sub B. What's different now is V sub C. Instead of this formula, we change over V sub C is equal to VC sat, which is 0.1. Because we're assuming this emitter is grounded, VC sat says 0 plus 0.1. So the collector voltage is 0.1 volts. Now I sub C is 9 volts minus 0.1 to 1K, which is 8.9 milliamp here. And then the emitter current is I sub B plus I sub C, 12.2 milliamp here. So it's a pretty good chance a problem like this will be on the final exam. At least one problem that involves a contradiction related to the circuit being in saturation. All right, we'll give some time to. Now these are there's multiple problems on this biasing, so you do want to start going through these problems. In another session or so, we're going to actually change over to MOSFET